Welcome to your flipped classroom, lesson 8.6. Now you can see from the title that today we are going to compare linear, exponential, and quadratic functions. And we've done this a little bit as we've gone through this chapter. I've reviewed with you what a linear function looks like, what an exponential function looks like, and we're going to put all of that into this lesson. The essential question says, how can you tell the difference between a linear, exponential, or quadratic function from a table of values? But before we get to a table of values, let's talk about the graphs. We have talked about this, and hopefully linear functions, exponential functions, and quadratic functions are something that you are starting to recognize. All right, a linear function is what we started with at the beginning of this year. Hopefully you are remembering that the first four letters in the word linear help us remember that the graph of a linear function is a line. Okay, we're also very familiar with the equation of a linear function. It's in the form y equals mx plus b. Exponential functions is something we learned more recently, but this is when your function has a power in it. So you can see right here, this is ab raised to the power of x. So when the function has a power in it, it's an exponential function. And we talked about how the shape of this graph is like a banana-shaped graph. And then the newest one, the one we've been learning in this chapter, is the quadratic function. It's a parabola. The graph is a parabola. And you'll notice in the equations that the quadratic function has an x squared in the equation. Okay, as long as the function has an x squared, it is considered a quadratic function, and the graph is a parabola. Now, in example number 1, let's plot these points and tell whether the points appear to represent a linear, an exponential, or a quadratic function. Just as a quick review, when you're looking at an ordered pair, the first coordinate is your x coordinate, the second coordinate is your y coordinate. So we're always moving right or left and then up or down. So we start with -1, 5. We go left to -1 and we go up to +5. To -1, we go right to +2 and down to -1. 0, -1. We stay in the center because our x coordinate is 0, so we don't go right or left. We just go down to -1. 3, 5, we go right to 3, we go up to 5. And for 1, -3, we go right to 1 and down to -3. Now, hopefully you can tell from the shape of these points that we are looking at a parabola. And if you want to draw it just to make sure that you're sure, all right, if we connect those dots, we do have a parabola. So this graph represents a quadratic function. Now I want you to take a minute, I want you to pause this video, and I want you to plot the points for B. See what you can do on your own and see what you come up with as the type of function. All right, so hopefully you graphed these correctly. Let's check and see really quickly. For -1, 2, you went left to -1 and up to 2. For -2, 8, you went left to -2 and up to +8. Now, -3, 32 is probably a little tricky because our graph only goes up to 10, okay? But we would go left to -3, and then we would go way up here somewhere to positive 32. So we'll just kind of guesstimate. We know it's probably much higher than that, but we're going to put it there for now, okay? 0, 1/2. We stay again in the center, and we go up halfway between the 0 and the 1, and then 1 and 1/8. So we go right to 1 and just barely above the line because 1/8 is a very small fraction. Now, hopefully, again, if you want to draw this, if you kind of want to connect these dots, you notice that this line would run right along that x-axis and then it would curve up. And of course, if we went all the way up to this point, way up here, and we put arrows, hopefully you saw very quickly and very easily that this is a banana-shaped graph, which makes this an exponential function. Now, differences and ratios of functions. How can I look at a table and tell whether the graph will be a linear function, an exponential function, or a quadratic function? All right, the good news is you've already learned how to tell if you're looking at a linear function or an exponential function. Remember when we learned common differences and common ratios? All right, so for the linear function, the first differences are constant. So basically you're going to find a common difference and you're going to make sure that it works all the way across your chart. So just as a review, remember you take the second term, subtract the first term, and see what you get. So for this table that they gave us, the second term is 8, the first term is 11, and that equals a -3. So when they tested -3 all the way across the chart, it worked. 11 minus 3 is 8, 8 minus 3 is 5, 5 minus 3 is 2, and 2 minus 3 is -1. All right, so you might want to add, because this isn't in the notes, basically if it's a linear function, there's going to be a common difference. Okay, there's going to be a common difference. And that leads us into the exponential function. There's going to be a common ratio. A common ratio. So remember, you take the second term divided by the first term for a common ratio. So in this problem, you take 2 divided by 1, and it equals 2. Now remember, when you find that common ratio, you are multiplying that number all the way across your chart. Never dividing, you're always going to be multiplying it all the way across the chart. So you can see when they checked that, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So it worked, all right? So if there is a common ratio that works all the way across the chart, you have an exponential function. Now the quadratic function is what's new and what's a little bit confusing. This says the second differences are constant. All right, now you can see from the first differences, there was no pattern. They figured out that to get from -1 to -2, they had to subtract 1. But then to get from -2 to -1, they had to add 1. And then from -1 to +2, they had to add 3. And to get from 2 to 7, they had to add 5. So there was no constant pattern. But instead of stopping, then they checked their second differences, okay? So let's talk about the first differences again. Basically, you would have to use your method of finding the common difference on every set of numbers. So let me show you what I mean. You would take the second term, which is -2, minus -1, and that would equal, that double negative becomes positive, that would equal your -1. Well, then you'd have to go to the next term in the problem, which is that -1. So -1 minus -2 equals, again, we got that double negative, which makes it a +1. All right, so we did the second term minus the first term. Then the next term on the chart became our second term, and we subtracted it from that term in front of it. So now we got to go to the next term on the chart, which is a 2, and we've got to subtract the term in front of it, which is a -1. So there's that common difference, or that double negative, sorry, that double negative. 2 plus 1 is 3. And then, of course, 7 minus 2, because we had to go to the next term on the chart and subtract the term in front of it. 7 minus 2 is 5. All right, so do you see how these numbers right here match these first differences? There's your -1, your +1, your +3, and your +5. Now, some of you aren't going to need to do all that work. You're going to be able to look at the chart and tell exactly what they did, and that's fine, but you have to record the first differences. You have to record the first differences. Now, those first differences become the new numbers that you're going to use to find a common difference. So if we take that second term, that +1, and we subtract that first term, which was a -1, it equals, after we change the double negatives to a positive, it equals 2. So let's check and see if adding 2 all the way across those first differences will give us the next number. So -1 plus 2 is +1, 1 plus 2 is 3, and 3 plus 2 is 5. So if the second differences are constant, it is considered a quadratic function. Now, before you feel completely defeated, let's go work an example. All right, example 2. Tell whether the table of values represents a linear, an exponential, or a quadratic function. So again, we can start by trying to find a common difference and then move to a common ratio and then move to the first differences and the second differences, or we can look at these charts and try to figure out ahead of time based on the numbers what we think it's going to be. So as I look at these, as I look at 1 to 3 to 9 to 27 to 81, it's pretty clear to me that they're not adding a constant number all the way across. So I'm going to go straight for the common ratio. So I'm going to take the second term, which is 3, divide it by the first term, which is 1, and I'm going to get a common ratio of 3. And that's what I'm going to test, okay? So 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. And 27 times 3 is 81. So there is a common ratio that works all the way across this chart. So this is an exponential function. So I never even have to graph this. I can tell just from the fact that there is a common ratio that this is an exponential function. Now let's look at letter B. We've got a 0, we've got a half, and then we've got a 1, and then a 1/2, and then a 2. So for me, these numbers are small and close together, so I am going to test for a common difference. So I take that 0.5, and I subtract that 1. I'm sorry, it was a 0. I subtract that 0, and I get a common difference of 0.5. Now I'm going to see if adding 0.5 all the way across this chart will give me the next number. So 0 plus 0.5 is 0.5. 0.5 plus 0.5 is 1. 1 plus 0.5 is 1.5. And 1.5 plus 0.5 is 2. So this chart has a common difference, which makes this a linear function. All right, hopefully you're with me so far. Now, letter C, okay? I'm looking at this chart. I'm going from 2 to 4.5 to 8 to 12.5 to 18. So honestly, my initial thought is a common ratio. So let's try it. Let's do 4 5/10 divided by 2. This equals 2 25/100. So let's try it. We know that 2 times 2 25/100 is going to give me 4 5/10. But what happens when I do 4 5/10 times 2 25/100? It gives me 10 125 thousandths. Okay, well clearly that's not what I needed. All right, I need an 8. So I can go ahead and cross out the common ratio, and I'm going to erase it from down here. So that means I've got to go try a common difference. I've got to go try a common difference to see if that works. All right, so 4.5 minus 2. 4.5 minus 2 gives me 2.5, or 2.5. So let's try that one. 2 plus 2.5 does give me 4.5. But does 2.5 or 4.5 plus 2.5 give me 8? That actually gives me 7. So again, I can cross out the common difference, which means there's a very high chance that this is quadratic. So I've got to find the first differences. So I'm going to do 4.5 minus 2, and that gives me 2.5. So I know that going from 2 to 4.5, I've added 2.5. Okay? Then I got to take 8 minus 4.5. Remember, we have to take the next term on the chart minus the term in front of it. So that gives me 3.5. So that next, I'm adding 3.5. So then I'm going to do 12.5 minus the 8 in front of it. So I've got 12.5 minus 8, and that gives me 4.5. So that means I added 4.5 right here. And then I got to take the last number on the chart minus that 12.5. And 18 minus 12.5 gives me 5.5. So you can see how getting from each number to the next was a completely different value. So now what we're checking for, can we find a common ratio on these first differences? So one more time, we're going to take the second term. Now remember, my second term is now my common differences that I found, okay? So I'm going to take 3.5 and I'm going to subtract it from the first term, which the term in front of it was 2.5. So I subtract 2.5, and 3.5 minus 2.5 is equal to 1. So here's our question. Does adding 1 to each of these first differences give me the next difference? So let's try it. 2.5 plus 1 is 3.5. 3.5 plus 1 is 4.5. And 4.5 plus 5.5, I'm sorry, 4.5 plus 1 is 5.5. So there is a common difference for the second differences. So this is a quadratic equation. Now, we will practice this some more in class tomorrow. So make sure if you have questions, you come in ready to ask them. But this is lesson 8.6.